Okay, so welcome back. And now we're going to go on to the next part for this one. And so for this one, what we're going to do is we're going to use these two Taylor polynomials to estimate the cube root of 11. Okay, so we know that we're going to use, this is the function, right? And we're estimating it using these two Taylor polynomials, the first and second Taylor polynomial, which is given by these two subsequent expressions. So let's go on and use these to estimate the square root, or excuse me, the cube root of 11. Okay, so now how are we going to do that? Well, since we want the square root of 11, that means x is 11, right? So we're going to stick in 11 for x. Okay, so we would say that using P1, P1 of 11, that's going to give us what? It's going to give us 2 plus 1/12, and it's going to be 11 minus 8, okay, which equals 2 plus, well, it's going to be 3/12, which is 1/4, which gives us approximately 2.25, okay? So that means the square root 11, right? So the square root, or the cube root of 11 then, is approximately equal to this, if we use this polynomial, so it'll be approximately equal to 2.25. If we use P2, if we use the second Taylor polynomial, we'll, let's see what we get. We get an estimate of P2 of 11, which then is going to be what? It's going to be 2 plus 1/12, 11 minus 8, minus 1 over 288 times 11 minus 8 squared. Okay, well, let's erase this. Okay, well, we already know that this piece here is 2.25, right? From here. And so then this piece becomes what? Well, this is going to be 3 squared, which is 9. So that's going to be 9 over 288, which 288 is divisible by 9. So we can reduce this. So this will be 9 over 288, which will reduce to 1 over 32. 1 over 32. Right? I believe that's right. Yeah. 9. Yeah, that's 32. So 1/32. Okay? So this is going to equal what? So we add those together, or subtract those rather, and we get 2.21875. Okay. So now what do we want to do? Now what we want to do is we want to find the bound on this. Okay? We want to use the Taylor theorem to bound the error. Okay, so how do we do that? Okay, so now we're going to use the uniqueness theorem of a Taylor series. So we know that there has to exist a C on the interval from what? On the interval from 8 to 11. such that what must be true? So that the remainder is going to be approximately the square root of 11 by the first Taylor polynomial, approximating the cube root of 11 by the first Taylor polynomials, which is going to satisfy R1 of 11. Okay, so again, by the uniqueness theorem, okay, of Taylor series, there exists a C in the interval from 8 to 11 such that the remainder, when approximating the cube root of 11 by the first Taylor polynomial, satisfies this. This is 11, because we have 11 here. Okay, now, so we do not know the exact value of C. Okay, so what we're going to do is we're going to find the upper bound of R sub 1 by determining the maximum value of the second derivative on the interval 8 to 11. Okay, so we're going to figure out what the maximum value of this is, right? So we're going to find what that m value, remember from the theorem, so we're going to find what the maximum value is of this derivative over the interval from 8 to 11. Okay, now, what is the second derivative? Well, remember, the second derivative is negative 2 over 9x to the 5/3. Okay, now, so now here's the thing. Since x is in the denominator, the largest this thing will be, okay, again, in absolute value, we're talking about absolute value. The largest that it's going to be in absolute value is when x is 8. Because x is on the denominator, so as x gets bigger, this is getting smaller. So as x gets smaller, this thing's getting bigger. So the smallest x can be is going to be when x is 8. Okay, so then we plug in 8, and we find out what that is. So we take the absolute value of this thing, right? Oops. So that's going to equal 2 over 9x to the 5/3. And so we're going to plug in 8 here. Okay. Last week. Okay. And so this is going to equal, what do we get? So it's going to be 1 over, well, 1 over 144, right? We got this one before, so this is going to be 1 over 144. Okay. And so now we can plug this in for m, right? So this is our m, right? So then we're going to plug this in for m. So the absolute value, right? So the absolute value of this is going to equal, is going to be less than or equal to, oh, let me do it this way. So we got that. So down here, so we can get the absolute value of r sub 1 of 11 is going to be less than or equal to m over 2 factorial times x minus, or excuse me, 11 minus 8 and so this is going to equal 0.03125. Okay, so the remainder is going to be less than or equal to this amount. Okay, so that's the maximum error for our estimate. Now we could do the same thing for R2. So let's do for R2. Okay, so let's erase this. You don't need this right now. Okay, so we got R1. Okay, so let's put this up here. So we know R1 of 11 is less than or equal to, or the absolute value of R sub 1 of 11 is less than or equal to 0.03125. So that's the first one. Okay, now let's go through the same process for R2. Okay, so we know R2 of 11 is going to equal f triple prime of c. So again, by the same reasoning, there has to be some c value between 8 and 11 such that r sub 2 of 11 is equal to this. Okay, and now we know, so again, we're going to take the maximum value of this because we don't know what C is. So we're going to find the upper bound for this thing. So we want to find the maximum value of this thing on the interval from 8 to 11. So now what we're going to do is take this derivative. So again, this is going to be f of x, no, excuse me, f of f of x, or f triple prime of x. And so this, if we take the third derivative of the cube root of x, we get 10 over 27, right? We get 10 over 27 x to the it'll be 8/3. Ugh. Now, again, the same reason applies. This is going to be maximized when x is equal to 8. Okay? Same as before. So, f triple prime of 8 is then going to be approximately equal to 0.0014468. Okay? So this is our m value, right? So this is m. That's our upper bound. So now we can calculate r sub 2, right? So now we know that the absolute value of r sub 2 of 11 has to be less than or equal to what? It's going to be m over 3 factorial times 11 minus 8 cubed. Well, we plug that in, and what do we get? We get the approximate error of what? 0.0065104. And that's it. So we know that the error, right, is going to be between here for the second, or the first polynomial, or excuse me, R1. So for the first Taylor polynomial, and then for the second Taylor polynomial, and so here's the difference in the error bounds for the estimate of the cube root of 11. Okay, have a great day.